How does a single equation explain the angle between vectors and their projections? Watch to find out. Hey everyone, welcome back to Curious About Science, the place where science meets simplicity. Today we're diving into a cornerstone of the vector analysis world, the dot product. And we're tasked with proving that the two definitions of the scalar product, r dot s as rs cosine theta, often known as the geometric definition, and the sum of the component products, 1.7, which is often the algebraic definition, are equal. One way to do this is to choose your x-axis along the direction of r. Strictly speaking, you should first make sure that the definition 1.7 is independent of your choice of axes. If you like to worry about such niceties, see problem 1.16, which we will get to in due time. Alright, so let's get started with this simple 2D example. Imagine two vectors, one aligned with the x-axis and the other at an angle theta, as we see with the r on the x and s in the xy plane at some angle theta. Now from the diagram, it's quick to see that the vector r has all of its magnitude in the x direction and none of it in the y direction. Writing this in angle bracket notation leads us to r and 0 for our components. Now, the vector s, which is somewhere in space, has some component in the x direction and some component in the y, as we see with the sx projection and the sy height. Now, putting these together, we get angle brackets of s sub x and s sub y, just like you would have in the introduction to physics class, breaking vectors down into components. Now, the components here are magnitude s and cosine. Since the sx is touching the theta, or the x-axis is touching the theta, this tells us this is our adjacent side, and the y is our opposite side. I don't believe in memorized cosine for x and sine for y. It's whatever the angle is touching goes with cosine, and the angle that's facing goes with sine. But nonetheless, we see that we have magnitude cosine, magnitude sine. And so if we're taking the dot product via the equation 1.7 from the algebraic perspective, we see that r0 and s cosine, s sine, dotted, r goes with s cosine, and 0 goes with s sine. But with 0, that component cancels out, so we can get rid of it. And thus, we simplify it down to the dot product r dot s is equal to rs cosine theta, which is equal to magnitude r, magnitude s with cosine. But this is the exact geometric definition. Okay, so we see how this connects their magnitudes and directions. It's like projecting one vector onto another, and this is what we see as a result. Powerful, right? But this does not cover every single situation that we need to. The simplified model needs to be extrapolated. So, but what happens in 3D? This is the next extrapolation. This is where the law of cosines comes in, and it generalizes the dot product formula for any spatial configuration that we need. Let me show you how to calculate this step by step so we can see how these two things bridge together. Now, according to the law of cosines, the side of this triangle, the sides, are related via this equation, where we have s minus r up here, represented there, where we have magnitude r squared, magnitude s squared, minus 2rs cosine theta. Now the goal here is to solve for the cosine function. And by doing so, we add this over to the other side of the equal signs, minus this difference here, and then divide by the magnitudes. Pretty straightforward right now. But we still have more work to do. But before that, if you are finding this breakdown helpful, give the video a thumbs up and share it with others who might benefit from it. Alright, so from the 2D example, we know that the geometric definition gives us the intuition, like the angles between the vectors that we've seen in previous videos, while the algebraic form, the summation, is the computational powerhouse. Both are two sides of the same coin. So now we need to show that these two sides are actually connected on the same coin. So starting with the geometric definition, r dot s, which gave us magnitude r, magnitude s times cosine of the two vectors, the angle between the two vectors, we know that the cosine we just solved for via the law of cosines. So now we can plug this definition in, which is what we see in the curly brackets here. Upon doing that, we see that the magnitudes cancel. So all we really have to worry about is the notion of the vectors here, which we don't have to worry about any specific type of geometric configuration. So we don't need to be aligned with an x-axis or y-axis or what have you. We can just compute it from here. Now, magnitude squared, if you remember from the definition of magnitude, which if it was just the vertical bars, that was square root of r dot r. But since we have a square, the magnitude squared just gives us r dot r and s dot s respectively. And same thing for this difference, s minus r. We need to take those because the difference of a vector is still a vector. Go see 8.1 to show the vector space axioms that solidify this. That being said, we still need to take these dot products in component form. And since we don't know what the components are, we have to generalize these forms to, say, Rx, Ry, Rz, respectively. Upon doing so, we see that this difference vector here, we're going to have to be very careful with the algebra because we end up with components squared. And since you have a difference, you need to FOIL them out. So for the full write-up, that will be posted on Patreon for everybody. But for here, we can see the landscape. And from the landscape, we see that once we distribute these, we get x squared, y squared, z squared in the r for the r vector, for the s vector. And then from here, after we simplify these square components, because what we would have is x sub x minus rx squared, and that gave us the square terms plus the cross term. And these are the summations of the cross terms here. But nonetheless, for the components squared themselves, we see we get a cancel here and a cancel there. The s's cancel, as we see with the yellow cancel bar. And then simplifying this, we get 2 canceling with the 2 here, giving us the exact form that we would want for the summation. So we started with a geometric object, which is the difference vectors for the law of cosines, and we showed that via component forms, we boil this down to the algebraic meaning. So clearly these two things are the same coin and tell us the same thing, but dramatically different implications in terms of what we're trying to do. Sometimes for things like, since dot products are everywhere, such as work being calculated, we can just take the angle between it and see that, okay, well, this amount of work is going to be less than that, and vice versa. So the applications of these are everywhere. And if you're into computers, 3D modeling uses this all the time. So definitely valuable to see that these two things are the same thing. Clearly, if you understand both definitions, it equips you well and gives you the tools to tackle the range of challenges that you will see, especially in physics, oh Lord, and machine learning at this rate. So, by the way, before we move on, the dot product has been talked about a lot recently in this opening section. We will also cover the cross product version of this exact same question in question 15, so hang around for that. Once we get the mathematical underpinnings, it'll be smooth sailing and we can focus back on the actual physics. But of course, in order to talk in the language of physics, we have to understand the language of mathematics. So that's the whole goal here, and we will plow forward. If you are passionate about understanding classical mechanics, hit that subscribe button so you don't miss my next video in the series. Huge thanks to my Patreon supporters. Your backing enables me to create in-depth physics content. Your support truly drives this channel forward. If you want to support our physics exploration, check out the Patreon link where you can find the problem PDFs and more in the description and join our scientific journey. As always, thank you for watching, and until next time, stay curious.